In this video, I would like to explore how current behaves in a few cases, starting with just a qualitative understanding of how it works, and then looking at some of the more calculational ways that we can think about it. All right, so the most basic model for a current is going to be just a river. So we often think of the behavior of electricity in relationship to how water might behave, which is okay in some cases and it's probably misleading in others. But our everyday experience with flows are, much more applicable to things like water than, we don't typically have a lot of experience with electricity. All right, so let me sketch just a sort of arbitrary shape of river like this. And it's going to have kind of narrow spots and then, wider spots again, like so. And if I wanted to express how the water is flowing in a river, I might do it with little arrows. So over here, maybe it has flows kind of like this, and then it turns. And as the river gets narrower, it might speed up. So I'll do longer arrows here to indicate that it's going faster through this narrow spot. And then maybe as it exits, it is going to slow down a little bit again and then be going more slowly again here. Okay, so this is a way that we could represent the flow. And it's a very local way to represent it. It's going to vary from point to point around the river. All right, so this way of thinking about it is what we call the current density. And current density is a vector quantity. So at each point, there's some amount of flow in a particular direction. We use J for that, and with a vector symbol. So you can think of that as a couple of different ways. So one way to think about it is I could imagine that I put a little net in the water, like this. And so I want to know how much water is passing through my little net. So in a way that's essentially the same as how we thought about flux before. I have this little area and I want to know how much flow is going through it. Now it's a literal flow rather than a figurative one like we had with flux. Okay, so in that case, what we want to think about is the amount of flow per area. All right, so then I could figure out the total amount of flow through that whole area by multiplying by the area, for instance. Okay, so that's one way to think about it. Another way that I can think about it, in the case of, let's say, electricity, is I can take the charge per volume. So just how much charge there is, the density of that, and then multiply it by the speed. So if it's moving in a particular direction, then that's going to be the direction of the flow. So I guess I should really have called this velocity. But this is the general idea for how we can think about the current density. Okay. So we've got two different ways to think about the current density. And let's talk about them one at a time. Okay, so for the first one, the flow per area, I can take the magnitude of the current density is going to be just the total current, which will be something like charge per second, and I'll divide that by the area. All right, so if this were not uniform, if it's a case like the river that I drew and it were varying as we went, then we might need to think about this in a slightly more complicated way. So maybe we would calculate the total current by integrating the amount of charge density times dA. Okay, so for each little piece of the surface, how much of the current is going through that piece. If the current is going along the surface, then none of it's going through. If it's going at some angle, then some of it's going through, and it will depend on the magnitude and everything else. All right, and one of the things that's kind of interesting about this is if I imagine that I have an area that captures the entire river, like this, and I do that at a few different points, well, what I'll find is that the amount of current has to be the same everywhere because the current's not getting used up and it's not being produced in some spot. So unless I have some reason or some physical mechanism that is removing charge or adding charge, which is almost never the case, that amount of current is going to be the same at all of the places. Okay, so the total current I, the total current I, the total current I, that'll be the same all over. Okay, so let's do an example of a quick calculation with this. So let's say that we have a wire with 1 millimeter radius. Okay, so that's a fairly ordinary wire. That might be a wire that is in the walls of your house. And let's say that it's carrying 1 amp. Carrying 1 amp. Okay, so let's figure out what the what the current density is in this case. All right, so we just use the formula, J equals I over A, which is going to be 1 amp over, well, the area of the wire, we want the cross-sectional area. So that'll be pi r squared, which is 0.001 meters squared. Okay, so when I divide 1 by this tiny number, I'm going to get a really big number. And so if you plug that into a calculator, I believe you get something like 3.2 times 10 to the 6 coulombs per meter squared second. All right, so that may seem like a weird unit for this density, but we can connect that back to the flow per area. So coulombs per second divided by the area. So amps per meter squared if you wanted. Okay, so let's look at the other relationship then. We also had this charge per volume times speed as another way to think about the current density. Okay, so if we consider that case, J equals the charge per volume times, now to be more specific, it should really be the velocity, not the speed. Like so. Well, essentially what I'm saying is, okay, so there's some amount of charge in this material, and it's moving with a certain speed. That's going to tell me the flow. All right, so let's, take this and write it in a slightly different form. So the way that the book presents this is that the current density is going to be E, the charge of an electron, times the number density, which is the number of electrons per meter cubed, times what they call the drift velocity. Okay, so we have a vector on each side, and so that part works out, and then the units will work out as well. All right, so for the example that we just looked at, let's say that we want to figure out what is the drift speed in that wire. All right, so specifically, how fast are electrons moving in a normal conducting wire? So we're going to use the same situation we just looked at, 1 amp and 1 millimeter radius. And I believe that if you were going to predict how fast the electrons are flowing in a normal electrical current, you would assume that they're going pretty fast. After all, when I flip a light switch, I don't have to wait 10 minutes for the lights to turn on. They turn on instantly. So let's see what we get if we actually do the calculation. Okay, it actually turns out to be something of a surprise. All right, so let's assume that the material that the wire is made out of is copper. That's a pretty normal material to use for electrical wires. So what we need then is the current density, which we already figured out. So 3.2 times 10 to the 6 coulombs per meter squared second. Okay, that's on the left-hand side. E is the charge of an electron, so 1.6 times 10 to the minus 19 coulombs. And then to find the electrons per meter square or per meter cubed for copper, you need a little bit more information. So it turns out that in a copper atom there are some number of electrons. I forget the number. It's over 10, less than 100. But not all of them are actually going to contribute to the current. Okay, so most of the electrons are going to be bound pretty tightly to their individual atoms, but some number of those electrons are able to flow from atom to atom. They're part of the sea of electrons, or the gas of electrons, that your textbook has mentioned before. And so it turns out this is a material property. Different materials will have different numbers of electrons per atom that contribute to the current. In copper, it happens to be about 1 electron per atom. So essentially what we need to do is we need to figure out the number of atoms per cubic meter of copper. And then since each atom is contributing 1 electron, we can use that number. All right, so I did that calculation, and what I found is that the number of electrons per cubic meter that contribute to the current is about 8.5 times 10 to the 28th atoms per cubic meter. All right, so again, all I did is I figured out the number of copper atoms per cubic meter using the density and Avogadro's number, and then I assumed 1 electron per atom. All right, and then the last bit that we get is the drift velocity. Okay, or in this case, the drift speed, since I'm not actually worried about the direction. All right, so if I solve for the drift speed, that's easy enough to do. You just plug it into a calculator, and what I get is 2.4 times 10 to the negative 4 meters per second, which comes out in the ballpark of 1 meter per hour. So, in fact, the electrons in a wire with some reasonable size of current are moving extremely slowly. And so it would take hours and hours for the electrons to go some large distance through the full circuit that is made in the walls of your house. So how does that make any sense? As I mentioned before, if I flip the switch, the current starts flowing immediately, and the lights turn on, and I don't have to wait for the for the electrons to get to the lights. Well, it turns out that the reason that happens, we can both have the lights turn on instantly, but also have the individual electrons moving really, really slowly, is because the wires are already full of electrons. So when I turn on the switch, the electrons start flowing everywhere. And because each electron pushes the ones after it, even though the individual electron is not going very fast, that whole motion starts simultaneously. So you could imagine that there was a line of cars, and this isn't exactly how this happens in real life, but if you imagine that there was a line of cars stopped at a traffic light, that once the light turns green, they all start moving simultaneously. They don't have to wait for the one in front of them to move. They all just move together. So maybe you could think of it more like a train or something, that once one starts moving, they all move together. There's no reason for them not to, because the wire is already completely full of electrons. Okay, so there's a difference between how long it takes an individual electron to get from one place to another and how long it takes for the flow to begin everywhere.